It all started with Sir William Thomson in the early 1800s when he tested a new theory that heat is simply molecules moving around inside of a substance. He conducted experiments that drew heat from warm substances, and he found that at some point all the kinetic energy could be drained from a substance, although he could never get close to reaching this point. Temperature is defined as average kinetic energy of particles making up matter. Also, kinetic energy is energy of motion. So, there must be a lowest possible temperature where all motion of particles in a substance stops. But recently, scientists have learned that small particles can never stop moving due to the rules of quantum mechanics. But absolute zero can still be defined as the temperature where matter is moving at the least possible amount. Unlike boiling and melting points, this point is the same for all substances. Sir Thomson then created a thermodynamic temperature scale which measures the amount of kinetic energy inside any given substance. This scale is known as the Kelvin scale, and scientists around the world still use this scale today. He created this scale by realizing, among with other scientists of the age, that when you hold the volume of an ideal gas constant, there is a direct linear relationship between pressure and temperature. Now, if you extrapolate this line backwards to the left, when it crosses the horizontal axis, it achieves zero pressure at about 0 Kelvin, or around minus 273.15 degrees Celsius. Now, I stated before that absolute zero means that the motion of particles is minimal at 0 Kelvin due to Heisenberg's uncertainty principle. This states that it is impossible to measure a particle's momentum and also the exact position at the same time. So even if you cool a bunch of hydrogen gas to the point where the particles have zero kinetic energy, then you would also know that their momentum would be zero. But measuring this is impossible due to the uncertainty principle. So true absolute zero is not possible. I will quote Dr. Dave Goldberg on another reason why you cannot reach absolute zero. It is because getting down to absolute zero has essentially the identical problem with getting up to the speed of light. Getting to the speed of light requires an infinite amount of energy, while getting down to absolute zero requires extracting an infinite amount of heat. Just to make it clear, both of these are impossible. Unquote. Now, the coldest natural object in the universe is the Boomerang Nebula, which is around 1 Kelvin. But the lowest temperature in all of the known universe was achieved back here on Earth in 2003. It happened at Massachusetts Institute of Technology, where they cooled a bunch of sodium atoms to 0.45 nanokelvin, which is 4.5 times 10 to the negative 10th Kelvin. The two most common ways that scientists reach near absolute zero temperatures were developed in the 1990s, which are evaporative cooling and laser cooling. Laser cooling works because photons have momentum, so when they collide with atoms, the atoms absorb the photon's energy. So, by shooting photons at atoms, when they collide head-on, then the energy of the photon gets absorbed by the atom, and the atom gets slowed down a bit. Then, each head-on collisions slow the atom more and more until it is barely moving. This is due to the momentum conservation principle. So since the photon's momentum was going in the opposite direction as the atom lost momentum going in the direction that it was going in. Evaporative cooling works by first using laser cooling, and then to get to even lower temperatures, they remove higher energy atoms while leaving lower energy atoms, which leaves a lower temperature substance. This is mainly done by using an instrument that forms a magnetic field which holds the atoms in a small space. And then the higher energy atoms will stay near the top of the field, and the cooler, more dense atoms will be near the bottom of the field. So it then takes atoms from the top layers until it is at the temperature that they want. Below about 30 Kelvin, some substances become superconductive, which allows them to carry electrical current with no resistance, which is extremely useful technology used in machines like MRIs. Then at temperatures around half a Kelvin, atoms don't collide like they normally do, and instead their quantum mechanical waves stretch and overlap, forming Bose-Einstein condensate, which becomes a single quantum mechanical entity, and quote, all the atoms act identically like a single superatom, unquote.